Okay, can everybody hear me in the online session? Okay. Can you please tell me what you see on the screen? That's great. All right. So let's start the session. Yeah. So today we want to continue our conversation about the theoretical part of this class. We're diving into theory of data graphics and talk about data in ratio and a couple of principles that we got that can help us to get rid of redundancies and so on. As always, try to cover your cough, wash your hands, and stay home when you're sick, and try to prevent touching your eyes and nose and mouth. We've got a couple of announcements. The first one is this ACM student outreach. If you're interested, please send me an email. The other one is this study that we are running together with Dr. Zhang, where we are interested to see the brain reaction to programming. And we're going to be using EEG, eye tracking, multiple picture cameras to monitor brain activities and eye movements. And we are seeking participants who have at least 6 months of experience with C or C++ programming, and they are older than 18. And if you're interested, send me an email. You will receive $45 to compensate you for your time for the 2 sessions that we're going to do with us. Any questions about that? No? Okay. So before I get to this, I'm not sure if you noticed or not, but I also released the final project. As we agreed last time, we combined the final project and homework 4 together, so that you can have more time to basically spend on that. There are 2 parts in the final project. The first part is asking you to reproduce 2 graphs. One of them is some sort of pie chart, the other one is some sort of bar chart. And then you will receive extra points if you use ggplot2. The second one, the second part that basically holds half of the mark for this final project is asking you to get a data set and do linear mixed model effects. Go through the steps that we covered in terms of visualizing it, taking a look at it, talk about it, figuring out what would be a good mix effect and what would be a good random effect. And basically discuss your choices. You're supposed to have at least 2 mixed effects presented. And you need to put a report on this. The report has to be minimum of 3 pages. But you're advised to elaborate as much as needed. So 3 pages is really the minimum. So try to talk about the steps a lot. So you need to put the graph and also your code. and your dataset, and if your dataset is too big, then you need to provide a link to the dataset. Now, you are welcome to use the dataset you use for your homework too, if you feel like that's an appropriate dataset. If it isn't, then you can just search for another one. It doesn't necessarily need to be big data. Whatever that can fit type of activity you want to do, make sure that you have a hypothesis before you start running these models. So there is a reason why something becomes dependent and something becomes independent variables. You need to have justifications. Does that make sense? Any question on that? So I gave you till the last week of the semester, I think. I think I put Monday 13th, which was supposed to be the time we are supposed to have our exam. And this is basically replacing that. So you've got something around a month to deliver this. And I think a month is more than enough to do something like this. But remember, if you face any problem that you couldn't solve, I'm here to help, so you just need to send me an email. But one thing that I cannot do is to basically start answering your questions on Saturday and Sunday, then the Monday is the day we want to deliver this. Okay? If somebody approached me for the first time on Saturday or Sunday, or I see your email for the first time at the very last week, I kind of consider it too late. I still try to help if I can, but most of the time when you hit a problem, we kind of need to do a face-to-face, hands-on thing. This is all programming, so I'm not sure how much I can help you over email. So it should be hands-on, and if you're approaching me the last moment, I'm sorry, it's too late for that. Okay? All right. Any question on that? Everything is clear? All right. Everything is clear online? All right. So let's get back to our lecture today. So we're going to start with this quote from Richard Saul Foreman. It says, everyone spoke of an information overload, but what there was, in fact, was a non-information overload. So we're going to start with talking about principles of graphical integrity. So what we put in here is first the representation of numbers as physically measured on the surface of the graph itself should be directly proportional to the numerical quantities represented. Then the second point is clear, detailed, and thorough labeling should be used to defeat graphical distortion and ambiguity. You should write out explanation of the data on the graphic itself, and you should label the most important events that you got in your data. When you do that, then it's as if you're putting a marker on somewhere on this data, on somewhere on this graph that you want people to pay attention to. So you set the values of the scene there, and that's very important. The next item is, the next principle is show data variation and try to prevent designing variations. Okay? So don't cause variation in your graphics. Just present whatever the data says. The next principle is in time series displays of money, deflated and standardized units of monetary measurements are nearly always better than nominal units. The fifth principle is that the number of information carrying dimensions depicted should not exceed the number of dimensions in your data. Okay? Don't create dimensions out of your data in your visualization that they actually doesn't exist. Okay? The data and your graphic should just represent whatever the data shows. Don't create a story out of it when it doesn't exist. Graphics must not code data out of the context. Now, sorry. Okay, so data graphics should draw the viewers' attentions to the sense and substance of the data, not to something else. The data graphical form should present the quantitative contents, and occasionally the artfulness of design makes a graphic worthy of Museum of Modern Art. But essentially, statistical graphics are basically instruments to help people reason about quantitative information. So we talked about this before. Playfair was one of the first people who invented the time series. So his very first charts basically devoted too much of their ink to graphical apparatus with elaborate grid lines and detailed labels. So this time series engraved in August 1785 is from the early pages of his major book that was called The Commercial and Political Atlas. Remember that for the first time in this book, the time series charts being actually presented, and all but 1 out of 44 charts that he presented in that was actually time series. There was only one chart that was not time series, and that was the very first bar chart. Before that chart, we didn't have anything called bar chart. So within a year, Playfair had eliminated much of the known data detail in favor of some cleaner design that focused attention on the time series itself. He then began working with a new engraved and a new engraver, and was soon producing cleaner, more clear and elegant displays. The improvement in graphical design illustrates the fundamental principle of good statistical graphics, which is above all else, we should always show the data. And this principle is basically the basis for theory of data graphics. Now, we talk about so first of all, the question always is how can we actually improve our graphics? And most of the time the answer is by minimizing the use of embellishments when you're using the graphical tool. But Professor Toft, we talked about him a lot in this course, and lots of these materials are actually coming from him. But he set these principles of graphical redesign. And these 5 principles are what we are going to talk about today. So the first one is talking about the principle that we just talked about, above all else, show the data. Then his second principle is to maximize the data ink ratio. Then the third principle is to erase non-data ink. Then the fourth one is to erase redundant ink. And then the fifth one is just revise and repeat. Keep doing this. You're getting rid of the stuff until you get to the level of perfection. Now, in terms of how to figure out what what is the data ink ratio, and how to erase non-data ink, and how to find the resultant data ink. These are the type of the type of topics that we're going to cover today. And we're going to dive deep into these principles of Professor Tuff and see how they can impact our graphics. Let's start with the data ink ratio. So, larger share of ink on a graphic should present data information, the ink changing as the data change. That's how it's supposed to be. So data ink is the non-erasable core of a graphic. The non-redundant ink arranged in response to variation in the numbers represented is what we call a data ink. So with all of that, we can get to this very simplistic formula. The formula said that the data ink ratio is data ink divided by the total ink used in the graph, which is equivalent to proportion of ink devoted to the non-redundant display of information, which is also equivalent to 1 minus proportion of graphic that can be erased without loss of information. Okay? Now, what do you think is the data ink ratio? Based on the explanation that I just gave and the formula that we just said, I can also ask this question in this way. How much of the redundant information you see in it? So redundant ink is going to be something that I can get rid of, and there wouldn't be any harm done in it. Anyone? What do you think about this?
Ratio is probably pretty high. Maybe minus those labels up there.
Do you know what does this shows actually? This is software. Do you know what this is graphic?
No.
This is 8E channel. This prayer signal. This is brain signal on 8 channels.
Is the M7?
Sorry?
Is the M7 the top one mean?
M7?
Yeah. On the top graphic, it's got RTR0 and then
Yeah.
M7.
Those are just labels. It's not just those, there are also these X's in here. In there. And these scales. These are all the labels. So basically, if you get rid of these labels, every other pixel that you get rid of are actual data. The labels themselves are also actual data. These represent the beginning of the events that are very important. Now, I've got no clue what does that M7 stands for, but it was apparently important enough for this particular data that they put it there. Well, yeah, I got no clue what is that M7. And also those labels that I've got, I also don't recognize any of those channels, so I'm not sure what they stand for. RT probably right temporal, RO is right, oh, right. I got no clue. right occipital. That doesn't make sense. How can a channel be on the right temporal and the right occipital? Anyhow, the levels are a bit weird, but for sure there were a reason. So nothing can be raised in here without losing information in these continuous 8-track of an electroencephalogram or EEG. The data change from background activity to a series of polyspike bursts, as you can see here. So what you want to have ideally is something close to 1 in terms of data in ratio, such as the electroencephalogram in here. Every pixel in here represents data except for the label. So there's nothing that we can get rid of in here. Does anybody know what are those markers for? Those pixels?
That like the start of an activity or something, something that's causing the brain to react differently.
There are two possibilities for that, either a noise or a sort of an activity. And they mark it. So later on, when they want to do an analysis, they are either probably gonna cut this thing out, cut that thing out, cut this part out, and then use the signal from there. Or if that represents the actual start of an event, then let's say an event is 1 second, and they're going to take 1 second from this point, and that's going to be the brain response to that event. So they take that from here, take that from there, there, and there. Okay? Now, here's another example. Let's look at the left graph. Most of the ink in this graph is data ink. The dots and labels on the diagonal are also part of the data ink. We perhaps 10 to 20% non-data ink, which is going to be the grid text and the data frame, and the whole frame. Then now let's take a look at the right graph. In this display, we nearly what we have is nearly all its inks are going to be devoted to matters other than data. The grid C overwhelms the numbers, and the faint points. How much of you see my, or you didn't see my? No one was pointing at all the time. Okay. So these small points that you're seeing here, you can barely see them. All here, they are basically scattered across this diagonal line. So what we have in here is another published version of the same data through the share of data ink up to something around 0.7, which is considered as an improvement compared to what we had before. In terms of maximizing the share of data ink, the larger the share of a graphics ink devoted to data, then you're obviously going to have a better ratio results. And what we want to do is to maximize the data ink ratio within reason. So every bit of ink on a graph requires a reason, and nearly always that reason should be that the ink presents new information. So the principle has a great many consequences for graphical editing and design. This particular principle makes good sense and generates reasonable graphics, reasonable graphical advice for perhaps something like 2/3 of all the statistical graphics. For the remaining 1/3 that this doesn't apply, the ratio is going to be ill-defined, or is just not appropriate. The most important thing, however, is that other principles bearing on graphical design follow from the idea of maximizing the share of data in. Now, the other side of increasing the proportion of data in is an erasing principle. This erasing principle is that erase non-data ink within reason. Ink that fails to show statistical information does not have much interest to the viewer of a graphic. In fact, sometimes such non-data ink clutters up the data and is and it's going to cause problems for us. Okay. So while it is true that boring ink sometimes basically helps set the stage for the data actions, it's surprising how often the data themselves can basically serve as their own stage. And whenever you've got redundant data in, what you've got is, in principle, something that that keeps repeatedly show the same number or the same value. So, in some sense, the label shaded bar of the bar chart, for example, they're all gonna present the number of to 6 different times. So these include left line length, right line length, shaded area, top line position, position of the number, and the value of the number. These all things, all 6 things are just basically presenting the exact same information in the graph. And in principle, you can basically start with the graphical display like what you're seeing here, and you can start get rid of bits and pieces of the data that are bits and pieces of ink that doesn't represent the data, or bits and pieces of the ink that just represent the exact same thing. There is no reason that you have to show the value of this bar being 12 6 times. One time would do it. So now we're going to go in a couple of slides. We're going to go through the steps that we're going to take that is going to convert this graph to the graph that you see on the right hand side. But before that, there is one small other thing, and that's an example of this. So here's an exercise for all. Can you tell me, based on all principles we learned in this class so far, what is the problem with this figure?
The dates at the bottom are kind of weird. It jumps every 3 years between each data point. And I first looking at it, I just assumed it was like a year each one. So it kind of lies, I guess, in that way.
What else?
the 3D effect they made to, so it kind of has that, I don't know, that like black shading in the background is really distracting to the actual data. It doesn't really add anything. It actually just makes it harder to read. You can't really see a definite where's the top of the line.
What else?
Fact that they use data ranges and all for their increments,
Sorry?
that they use ranges for their increments instead of fixed values.
You mean the label on the down?
Yeah.
Yeah. What else?
The curve effect makes it look like it's different value changing throughout the year.
What else? Now, be honest. Could you actually see all of these problems before coming to this class? Or you would just look at this and say, oh, this is beautiful, right? Good. If you couldn't and now you can, that's great. Now tell me what else is the problem. You want to give me something?
I don't know what the graph is showing. There's no labels on the axes. So
Yeah. What else?
yeah, you can't think of
They already say all of the easy ones, right?
Yeah.
And then the difficult one for you.
Sorry.
So, there's a problem in here. Look at all of these curvatures. These curvatures are different from each other. And it's not clear how does the difference between the curvatures impact everything. Now, in here, the curve starts there and finish at 100. In here, it starts at whatever this number is and finishes in 0. Right? And that doesn't make sense. It's not clear what does it show exactly. So it's as if there is another dimension to this data that we just created out of nothing, while the data doesn't have that dimension. But you can also interpret that in a very different way. And for some obscure thing, you can say this is a 1-year data, but the others are showing the equivalent on year 1943, 4 years or 7 years, whatever it is. 4 years. 4 years after the start of this, showing an equivalent value there, which the data actually doesn't show. The data is only showing that one. Only that, there is nothing else that it shows. It doesn't show what happened between here, 1939, and 1943. It only shows what happened between 39 and 40. This 1-year data. We technically didn't even need to know the next year in here because everything is just 1-year format. If we know the starting point of the data, the end of the data is going to be 40. It's not going to be here. So it's as if you wanted to put all of these numbers in here in detail, we cover everything, then we could have converted this to a bar chart, a bar plot with a lot of bars missing. Because we didn't have any information between 40 to 41, 41 to 42, 42 to 43. Right? That's the same for all of this. So there are all of these problems and all of these dimensions being presented in here just because they wanted to look disparate. So they created all of these extra dimensions to a very simplistic data that didn't have any of these dimensions. So remember, the ink should always present data. You should not create a story out of it when it doesn't exist. Okay? So these principles of Professor Toff are quite useful and quite important. Now let's get back to a couple of other things before we get to how to get from this graph on the left to the graph on the right. But here's another thing. I'm just going to set the stage for that exercise. So most of the time we've got bilateral symmetry of data measures. And they also create some sort of redundancy. The example is in a box plot and the open bar and the chain of faces. So half face basically carry the same information as the full face. Halves may be easier to sort by matching the right half of an unsorted face to the left half of a sorted face. And this is going to be easier than to look at the full faces actually. The bilateral asymmetry doubles the space consumed by the design in the graphic without adding any new information. The few studies done on the perception of symmetric designs indicated that when looking at a vase, for instance, a subject would basically examine one of its symmetric halves, glance at the other half, and seeing that it was identical, sees his explanation. The enjoyment of symmetry lies not with the physical properties of the figure. At least our movement suggests anything but symmetry, or the balance, or anything else. Now, we want to talk about the other principle about erasing the known data inch within reason. So, in fact, we want to talk about redundancy today. So, I just spoke on about how symmetric information and designs basically waste a lot of ink, right? But on the other hand, sometimes that semantic information that would create redundancy for us are actually useful. So redundancy upon occasion has its uses, giving context and order to the complexity, facilitating comparisons over various parts of the data, perhaps creating an aesthetic balance. In cyclical time series, for example, parts of the cycle should be repeated so that the eye can track any part of the cycle without having to jump back to the beginning. Such redundancy possibly improves this Marie's 1880 train schedule that we see here. Those people leaving Paris or Lyon in the evening find that their trains run off the right-hand edge of the chart to be picked up on the left-hand side of it again. Now, if we wanted to fix this, we could have created something like this. So consider the repeating of the train schedule. Here, the wraparound helps the reader see the continuum from late night through the morning. And attaching an extra half cycle makes every train in the first 24 hours of the schedule a continuous line. It's as if you're mounting it on a cylinder. It's as if you're basically mounting this thing on a cylinder that will connect the two sides together, so they can just carry on it. Now, here's another example that you're probably very familiar with. Not this version of it, but things like this are very familiar. So in here, instead of once around the board, in this display of surface ocean currents, 1 2/3 times around is going to be a better one. So most data representation, however, are of a single complicated number, and data graphical repetition is going to be needed. So the idea is, unless redundancy has a distinctly multi-purpose, the second erasing principle always applies, which states that erase redundant data within reason. Now, let's get back to that example that we were looking at. So, just as a good editor would basically ruthlessly prunes out unnecessary words out of the document, so a designer of a statistical graphics should basically prune out ink that fails to present fresh data and fresh data information. So although nothing can replicate, nothing can replace a good graphical idea applied to an interesting set of numbers, editing and revisioning are as essential to sound graphical design work as they are to writing. So T.S. Eliot basically emphasized that capital importance of criticism in the work of creation itself. Probably, indeed, the larger part of the labor of an author in composing his work is critical labor, the labor of sifting, combining, constructing, expunging, correcting, testing. And he says that this frightful toil is as much critical as creating. Now, let's consider this display that we've got in here, which we basically started the whole conversation with this. So, in here, we're comparing each long bar with that just a short bar to show the viewer that under the various experimental conditions, the long bar is longer. That's all the message that we are trying to convey with this particular graph in here. Now, vigorous pruning improves the graphic immensely while still retaining all the data of the original. It is remarkable that erasing alone can work such a transformation from this to this. The horizontals indicate the paired comparisons and would change if the experimental design changed. So they count as information carrying. All the asterisks are out since every paired comparisons were basically statistically significant, and that's what the asterisk is supposed to show. This is a point that you can just make by putting it inside the caption instead of adding a stuff into the graph. So here is the mix of no data ink and redundant data ink that was erased about that would basically erase about 65% of the original graph. And it's going to give us when we get rid of this, then we're going to be left with a graphical display like this. So the data graphical arithmetic looks like this. The original design equals the erased parts plus the good part. So these two, the erased part plus the good part, is going to give us the original one. But if you get rid of the redundant, unnecessary part, then you can basically transform a bad graphic like this ink is representing the actual data without any additional information and without any repetition. Here's another example. Now, this graphic drawn by the distinguished science illustrator Roger Hayward shows the periodicity of properties of chemical elements exemplified by atomic volume as a function of atomic number. The data ink ratio is less than 0.6, lower because the 76 data points and the reference curves are obscured by the 63 dark green marks arrayed over the data plane like a precision marching band of 62 mosquitoes. Now, the grid ticks compete with the essential information of the graph, and the curves tracing out the periodics and the empirical observations, and the little grid marks and part of the frame can be safely erased from it. And as a result, we can get something much better in terms of data ink ratio. We can get to something like this. From something like this, we just get rid of these. We can end up with something like this. So the unquartered display here brings out another aspect of the data. Several of the elements do not fit the smooth theoretical curves all that well. The data ratio has now been increased to something around 0.9, with only the frame lines remaining as pure known information. If you get rid of these, then we are going to get to 100. Now, the reference curves prove essential for organizing the data to show the periodicity. The curves create a structure, giving an ordering, a hierarchy to the flow of information from the page. Now, restoring the grid fails to organize the data. The ticks are going to be too powerful, and they also add a disconcerting visual vibration to the graphic. With the ticks, the reference curves become all the more necessary, since the eye needs some guidance through the maze of dots and crosses. The space opened up by erasing can be effectively used. Labels for initial elements of each period. And an alkali show the beginning of each cycle in the periodic table of elements and in the graphic. The unusual rare earths are indicated in here. In addition, the label and numbers on the vertical axis are turned to read from left to right rather than the common approach where they read it from bottom to top. And that basically made the graphic slightly more accessible, a little more friendly. Now, the last thing that we want to talk about today is going to be the steps in designing the visualization. There are going to be 6 steps. Starting with intuitive mappings from the data, then selecting and modifying the views, then controlling information density, then work on keys, labels, and legends, and decide to add them and how to add them and so on. Use color with care. We talked about that before. And then capture the importance of aesthetics. Now let's go through them one by one. The first one was intuitive mapping from the data. You need to consider the semantics of the data. You need to consider the user's domain-specific mental model. You need to consider the spatial attribution, like latitude and longitude. You need to consider time. You need to consider standard use of color for that particular data. Some data come with some restrictions on what sort of colors you can use. For example, if you're using brain data that is supposed to indicate activity or tumor or whatever, you don't get to show the brain in red and show the activity in gray. Because the common sense is the tumor stuff is supposed to be red, because red is supposed to show something bad. So the common sense is important. It came up during the discussion that we had on the color, and it's coming up in here again. So use the standard use of color. Okay, don't invent new color schemes for yourself just because you like them. Okay, it doesn't matter if you like something. What matters is are your audience gonna be willing to look at it? Okay, you create graphics for your audience, not for yourself. The next one is proper mapping of attribute types to visual feature types. The attribute types are going to be nominal, discrete, continuous, and visual types are going to be color and size. And also remember that non-intuitive mappings may reveal something informative. So sometimes you have to try it. Make sense? Yes? No? Is the second step in designing visualization, which is selecting and modifying views. You have to allow options to explore different views, like GPS systems. Allow panning and zooming of the visual and of the data space. Allow color map selections, and you should allow escape control. The third step is control information density. You should add, we talked about that before. More is generally better, but too much information can also lead to confusion. And you should try another visualization rather than just putting everything on top of each other. Okay? Don't try to minimize the number of graphs you're going to have whenever you want to report something. If you need a new graph, just create a new graph rather than trying to combine 2, 3, or 4 graphs into one display. It's going to become more and more difficult to read them, and sometimes that results in some comparisons that the data doesn't support. Okay, so you end up creating some dimensions in your data, some correlations between different graphs that not necessarily have any correlation with each other. It's just it shows in the graph that they are kind of correlated, even though in reality they are. These things become much worse when people use different scales for different graphs, and then they put them over each other on different layers. That's a stupid thing that some people do. And you can find a lot of examples like that in scientific papers. The people lay over different graphics on each other with different scales. And that results in finding some sort of correlation between data points and within those curves that actually doesn't exist. And it doesn't make sense, and it shouldn't make sense. Okay? So that's very important. Then use the same ink to serve more than one purpose. The point itself is a number or classification symbol. While striving to convey more information, be sure that is balanced by understanding that the graphic does not become a puzzle. Okay? If you create something that your audience require a couple of minutes to figure out what the hell you're trying to tell, you just fail because nobody's gonna bother. Okay? Yes? Okay, so if the viewer asks, what am I looking at? Then the visualization should be resolved. You just failed it. If somebody look at it and says, what the hell is this? Start over. Okay? The next one, keys, labels, and legends. So sometimes grades and ticks and the tick marks can actually help, and sometimes they can hinder. You can create something like this, or you can remove them and create something like this. If your intention is to show some sort of correlation over time, then you don't necessarily need to have ticks. You just need to show the patterns are changing in respect to each other over time in the same manner. Now, the same manner can be positive or negative because you can have a positive correlation or negative, meaning that in something like this, you can have a case where in here it starts from top and in here it comes to down. That's a negative correlation. In here, everything is a positive correlation. It's almost correlated, almost phase lock, time lock. Okay? So you don't necessarily need to have the legends. But then there are times not having the legends are going to cause a lot of problem. What if I wanted to show the change in response to some of the differences in the change in response to an event? Okay? Now, if I don't have the marker of the time in here, and if I don't have the marker on the magnitude of the signal in here, then I cannot compare the magnitude of the difference between these 4 different waves. So it very much depends on what you want to show. Sometimes it's very important to have the text and the legends and the labels, and sometimes it's better to just get rid of them. Just make sure that you get rid of something that doesn't hurt the message that you want to say. And if it does, then you shouldn't get rid of it. Here is another example, set of examples. You can have something like that with everything, which is absolutely ridiculous. Nobody can actually read that. Or even barely you can see the points. Or you can have something like this, much clear. You see all of the measures there, the important measures, and you can probably come up with the other measures that you don't see. Or you can go with something as simplistic as this. Depending on the message that you want to convey, either this or this is going to work. One thing that is definitely not going to work is that. Make sense? Now, another example is in here. You could have all the numbers and all the ticks, or you could basically remove half of them and create something easier to follow. Okay? So, more lines and more information you present on the graph, more confusion you are going to cause in terms of what is the important thing to look at. You try in a non-expert eye, they try to find a meaning between this line and these things, and this line and these things. If there is any meaning between this point and this point. Realistically, there might not be any meaning whatsoever. But instead of finding the actual message that this graph wanted, then they spend time trying to find the patterns that doesn't exist. Now, if you remove them, then there are less patterns to look for, and it's easier for them to find them. Make sense? Next example, which is really the same thing. We reduce the number of grids in here, especially the horizontal one. We get to a representation that is much better. If I don't have any information up in here, there is no reason for me to show these at all. If this is the only graph, if I've got 10 graphs of 10 different experiments or 10 different set of data that scale in the same way, and some of them already have information in here, then it's important to keep it in the same scale. Everything should be in the same scale so you can compare these multiple graphs with each other. That you can see in a lot of scientific papers all the time. But if it is a single graph, and if there is no information there or here, there's no point in showing them. So you cut those out, and you're left with the ticks and grids that are important, that convey message and information. Yes? All right. The next step is use color with care. Be careful about using bad choices of color map. Sorry. colors confused by those with color blindness. And the cases where you just have ridiculous number of colors. They become so close to each other that it's difficult to distinguish different colors from each other. They all going to look red and green in here, even though there are multiple reds, multiple types of greens. Now, the last step in designing visualizations is the importance of aesthetic. It gives you the focus on the data, they balance the presentation, and they help with the simplicity. Any questions? No? All right, so last thing that I wanted to mention before we finish our class today is about next week. It's not 100% guaranteed yet, but we might have to cancel either Monday or Wednesday next week because of an operation that I have to take my wife to Denver, and it's not going to be possible to come back in time. Yeah, based on my calculation, we are actually ahead of the schedule because we spent less time on R this year. And the reason for it was that I completely changed the R lectures compared to last year. So that it become more direct. So because of that, we are ahead of the schedule. So hopefully canceling this class is not gonna cause any problem. And I'm not in favor of canceling classes. This, in fact, is going to be the very first time I'm canceling class. I've never canceled a class before. Those of you who have been with me in other classes, you know this. So I'm going to let everybody know, hopefully, in Saturday or Sunday, when they informed us. They are testing us. When they informed us if this needs to be done ASAP or not. So if you have to cancel, we cancel. If you did, please use the time to start working on your final project. If you haven't taken a look at it, take a look at it. It's gonna take a fair amount of effort. It's not an easy thing to do, it's gonna take time. So you need to spend a lot of time on that to find your data sets, to figure out how to basically put those two graphs together to look alike and so on. Any questions? No? All right. I hope you enjoy the rest of your day. See you all next week.